Use the standard results for the sum of r squared and the sum of r to show that for all positive integers that this is true. Now, I would say to learn both of these results, you actually get given the sum of r squared in the formula book. You will need to learn the sum of r. It's a half n plus 1, the nth term of the triangle numbers, in fact. Okay, let's get into this. We've got the sum from r equals 1 to n of 2r minus 1 all squared. And the first thing I can do is expand that bracket. It's going to give me 4r squared minus 2r, so minus 4r plus 1. Technically, there's a bracket around this one. And now I can separate it into the different summations. So I can bring the constants out of the summation, remember? Because I can either, times each term by 4 and add them up, or I can just add them all up and times by 4. I'm factorizing it out, essentially. So this will become r squared. This one is r. And I'm just left with the sum of lots of 1's. Okay, now I can apply my formulae. So I've got a 4 times 1/6 n plus 1 to n plus 1 minus 4 lots of a half n plus 1. And don't forget this last one is actually me adding up n lots of 1. I'm going to be adding n. Okay, this will become 2/3. And my final answer, I've got a third. Okay, this one will become 2. So I'm going to straight away factorize out a third n. Remember, that isn't the final answer. Then I'll just be left with a quadratic term that I can simplify. So I'll have 2 times n plus 1 times 2n plus 1 minus, now when I factorize a third out here, I'm going to need to times 2 by 3, so I'm going to have 6. Okay, because that will mean I'm left with 2 when I multiply it back out. So 6 times n plus 1 and then plus 3, because I'm factorizing a third n out, I'm going to be left with that 3. Right, it's got to tie this up now. I'll write it as n over 3 because they did. Okay, so let's multiply this bracket out. 2 lots of 2n squared plus n plus 2n, so that's 3n plus 1 minus 6n minus 6 plus 3. This becomes 4n squared plus 6n plus 2. I've got 4n squared, the 6n and the minus 6n cancel. I've got a minus 3 plus 2. It's going to be 4n squared minus 1. That is our final answer. Hence, determine the sum of the squares of all positive, odd, 3-digit integers. Let me just grab that and bring it down. Okay, so let's not forget. Let me just also copy this. This is what we've just shown, which obviously going to be using that in a second. Okay, the sum of the squares of all positive, odd, 3-digit integers. So the first one would be 101 squared. Then I'd be adding 103 squared all the way up to 999 squared. But these here are odd integers as well, because 2r minus 1 will definitely be an odd integer. So I just need to think about what my limits are going to be. So let's just let 2r minus 1 equal 101. Then 2r will equal 102, and r will equal 51. That's going to be my lower limit. My upper limit, 2r minus 1 equals 999, is going to give me r equals 500. So I want to find the sum from r equals 51 to 500 of 2r minus 1 squared. That is precisely going to give me the sum that I want. Okay, well, I have the sum from 1 to n, and I want 51 to 500. So I'm first of all going to do 1 to 500, and then just subtract the ones that I don't want. So 1 to 50. Remember, I want to include 51, so I'm only going to subtract up to 50, then I'll be left with 51 onwards. That's everything we need, because now I can just sub in n equals 500 for the first one. 500 over 3 times 4 times 500 squared minus 1, and subtract 50 over 3, 4 times 50 squared minus 1 for that second one. And we can put this into our calculator. We get, when I did it, I worked out this term here. So 999,999 minus 50 over 3 times 9999. Then that becomes 1666. There's 5 sixes, 500 minus 1665. Oh, sorry, 50, 16,600. No, there's 3 sixes, sorry. Okay, and ultimately that gives an answer 166,499,850. 166,499,850 is the sum of the squares of all positive odd three-digit integers.